And then we put energy and entropy, okay? We put energy, both divergent kinetic energy and vortical kinetic energy at the system at the largest scale, which is, at the smallest scale, sorry. And then the question is, does this cascade upscale? Okay? And we'll also ask how this turbulent cascade depends on the forcing, how you enter it into the system. Because you can force, so you can force vorticity, you can force divergence, you can force temperature or moisture fields, variability in these fields, and these excite both divergent and vortical energy. Okay, so we're going to use a tropical planet, as I said, where there's no baroclinic instability. So you have no sea surface temperature gradients, and you have one sun heating the whole planet. Okay, and we're going to force at very small scales, or at mesoscales. And we are going to have moisture, and we'll vary the degree of moisture coupling. So moisture can be advected passively, but it can affect the temperature field when it condenses or evaporates. And it will be very simple moisture. And we've done this using a shallow water model with stochastic forcing at mesoscales and Newtonian damping. Very simple moisture. And we've looked at moist aquaplanet GCNs. But I'm only going to talk about the shallow water model in this talk. Okay, so we have our equations. Okay, the shallow water equations. There's also a moisture equation. What we have is momentum damping here with a very long time scale. And we have thermal damping. It could be considered thermal damping, a damping on height with very long time scales of 500 days. And we have different evaporation and condensation time scales. We've played around with this. So there's a moisture equation, and there are sources and sinks of moisture. Q plus is when the moisture is above some saturation level, and this is when the moisture is below. So when it's below, you have evaporation, you add moisture. When it's above, you condense, you take away moisture. There are forcing terms, stochastic forcing terms, that can go into any of these equations, and we play with them separately. Okay. So just physically about the model, a shallow...
It appears both in the moisture and the height?
What?
The Q's appear both in the moisture
yes.
and the height?
Yes, so I'm coming to this, just the physical interpretation, a very simplistic physical interpretation of the shallow water model for the tropics can be the lower layer of a two-layer model, okay, where this is the thickness, and if you have a wave that is cold here and warm here, the overall column is colder when the depth is high. So a large H is cold, okay, and a small h can be, so this is like a two-layer two equal potential temperature layers. And so a shallow region is anomalously cold. And so
the height and the moisture obey almost the same equation, same for the
right.
relaxation term.
So the thought is that most of the moisture is here, and when you have convergence of moisture, yeah, you have a condensation, or when you have more moisture than saturation, you condense and release latent heat, and that will actually warm the layer, and so the height will decrease. Okay? It's like a negative source of height. And the opposite is true when you evaporate, you cool and you thicken the layer. So it's the simplest effect of moisture. Moisture comes into the height equation, which is temperature, through latent heat release or taking. Okay? Okay, so we're going to look at different types of forcing. Vorticity forcing can be viewed as small-scale unresolved dynamics, so the effect of gravity waves on momentum, for example. It's like placing random vortices. Divergence can be viewed as the divergence or convergence in convective events. Okay, they force this vertical flow, which is causing horizontal divergence and convergence. When we force the height field, you can look at it as small-scale heat sources. And forcing moisture is like what you have with small-scale tropical systems. They add or take moisture from the system. So none of them are forcing alone are really physical, but still, if you have these convective systems, they affect all these variables, and we want to see what the effect of each is on the model. Okay, and what turns out to be, we force one variable, but then we can look at the equilibrated levels of vertical kinetic energy, rotational kinetic energy, potential energy, and latent energy. And this is what we get. Okay, so we have 7 different runs. For the dry, we have vorticity, divergence, and height forcing. And for the moist, we have vorticity, divergent, height, and moisture forcing. And these dots show the level of energy you put in, and then you have the level of equilibrated energy. And one thing we note is that the level of vertical energy varies. Okay, this red line varies a lot between these runs.
You have only one-way interaction. Yeah, you don't take into account, for example, the downscaling of the entropy should in some way affect the vorticity source.
The source itself, no, it's just stochastic forcing. It's small, okay, and we put it in, and in most cases you will see that the stochastic forcing is not dominant in the variability itself. Okay, but we can have cascades to smaller scales and larger scales than the forcing, but the forcing itself varies stochastically between time step to time step. So yes, there's no feedback into, I can't study the coupling, convectively coupled waves, because there's no feedback to the convection. Okay, so if we take these energy levels and then we can place them here in terms of whether you're forcing vorticity or forcing divergence. So dry divergence forcing forces divergent energy only. Moist divergent forcing is closer. There's maybe tiny bit of vertical energy that gets forced. And it's weaker, mostly it's weaker divergent forcing, because when you have convergence, for example, and rising, then you have adiabatic cooling, but moisture condensation will counteract this with warming. And so the effect of divergence is made weaker on temperature, is weakened by moisture. Okay? You can force height. This is what Garfinkel and Shamir et al. Did, forcing the height field. It excites somewhere in between both divergent and vertical energies. Moist height forcing excites vorticity stronger than dry height forcing. Moisture forcing forces vorticity very strongly. And then there's moist vorticity forcing and dry vorticity forcing. Okay, so this is how we place them in this diagram. And now I'm going to talk to you about the, as I said, the key is to force vorticity, the most efficient upscale cascade exciting case when we force vorticity in the dry model. Okay, so what you see here, this is now the zonal wave number. Sorry, the total wave number. Here it's the zonal wave number. And this is the eddy kinetic energy. In red is the rotational kinetic energy. In blue is the divergent kinetic energy. And the gray is the sum of both. And this is the forcing scale. Okay, I left this here, but this is the scale at which Garfinkel and et al. And Shamir et al. Forced slightly higher, lower wave numbers. So we force it wave number, total wave number 100. And it can be zonal wave number 0, but wave number 100 in the meridional direction, and it can be wave number 0 in the meridional direction and wave number 100 in the zonal directions, and all the combinations between. Okay, so, and you see that when you force vorticity, you're exciting divergence at the forcing scale. You're exciting, you see the forcing as a peak, but you see the maximum energy is at a smaller scale. Okay, and we've checked explicitly, there is an upscale cascade, and this is the minus 5/3 slopes here. Okay, and this is the radius of deformation. This is where it halts, the cascade. And here you see a Wheeler-Kiladis diagram, as I showed you, only now we're showing not the symmetric component, but everything. And so you see this mixed Rossby gravity wave also appearing, and you see both red noise background spectrum and Rossby waves. You see some Kelvin modes, mixed Rossby gravity waves, and inertial gravity waves here. Okay, so we are able, from this forcing at mesoscales, to excite both the red noise and these waves. Okay, it's interesting to see we can turn off rotation in our planet, and what happens is the halting scale grows, because when you have no rotation, the Rhine scale, the radius of deformation becomes infinite. And so it can't be what's halting the cascade. You still have a maximum here at some scale, and we think this is just the dissipation scale that halts things. It could also be the geometry maybe, but probably the dissipative scale. Okay? Now, if you force divergence, this is what you get. So it's only showing this bit. Okay? But you see that the peak, first of all, you have much more divergent than rotational energy. But for both, the peak energy is at the forcing scale. No upscale cascade. Okay. So this is the picture we get. We put vorticity forcing in. The vortical kinetic energy shows an upscale cascade. Okay? All along, because it's a shallow water model, you're forcing divergent energy. Okay? These modes have divergence and rotation together. So you have most divergent energy at the largest scales, and then it has to cascade down at some level. As the divergent kinetic energy also shows a minus 5/3 slope. Okay, and the question is whether this minus 5/3 slope for the divergent energy is because we're forcing it as a minus 5/3 slope from this energy, or it might be a 3D downward cascade, 3D turbulent downscale cascade, which also has a minus 5/3 slope, or something else, and we don't know, and we haven't really looked into it further. But it's interesting. Okay, so now we add moisture. And this is the same plot you saw here. So you see the maximum energy here at divergent energy is at planetary scale. And this is the moist run, the same plot, but for a moist model. So we still force vorticity. And there are a few differences. So first I will say that to make our model more realistic, we reduce the radius of deformation for the moist runs. We reduce the shallow layer depth for the moist runs. So that reduces the radius of deformation, but also the moisture itself, because the radius of deformation depends on the temperature response, moisture itself, by counteracting adiabatic heating or cooling, also reduces the radius of deformation. So there are two reasons why the radius of deformation decreases, but in any case, it halts the cascade at smaller scale. So this is where the dry halts, and this is where the moist halts. So that's one difference.
Is this logarithmic scale?
Yes, sorry. This is logarithmic scale, and this is logarithmic scale.
So on a log scale, it's about the factor of 2
Yeah,
or something?
it's something like that. So this is 10, and this is 20, maybe less even than a factor of 2. It's not a lot, but it's still there. And the depth is reduced from 100 meters to 50 meters, actually.
And the purple is the moist, right? What's the purple?
Okay, the purple is the peak of the dry here. This is divergent kinetic energy, and this is the peak of this dry run, and this is the peak of the moist run, and I've put them both so you can see how they
So
should.
somehow the peak on the right-hand side of the moist
Yeah.
is...
No, the right-hand side is dry run.
Right,
This is
but
moist.
Okay, the peak on the moist is smaller than that.
Yes,
Oh, this is
smaller
nice.
scale. I know, I told you it's a heavy talk, right? I told you it's a heavy talk, lots of detail.
Sometimes we can't carry so much weight.
Okay, the main thing is the cascade halts at smaller scales in the moist run. Okay, also you can see that divergence is excited more strongly in the dry run. Okay, as I said, moist processes weaken the divergence because of the diabatic heating that occurs when you have adiabatic cooling. And also the planetary scale waves are excited more strongly in a dry run compared to a moist run. But these are the differences. Overall, it's the same. Okay? Now, what happens when you force moisture or you force height in these runs? Okay, moisture forcing is very efficient in exciting an upscale cascade. It's hard to see that it's more efficient, but if you look at the time evolution, in the moist runs, you're already at this you start with a peak like this, and then it evolves up. In moisture, this happens right away. When if you force moisture, if you force vorticity, it takes longer. Okay, we're not sure why. We have some.
I can't say, is it 1 decade between the two numbers on the abscissa? It's 1 decade between, no, on the abscissa, not the ordinary.
Here,
The tick labels.
Yeah,
this is 10 and this is 100.
So it's 1 decade.
Yes,
Wow, okay.
it's like
So
one
it's
decade.
about half
Yeah.
a decade if you have the minus 5/3.
Yeah,
So,
right. It's very little. You're right. And for height forcing, we say it's less efficient in exciting an upscale cascade because still the peak, at least in divergent energy, most of the energy, the strongest energy is at the forcing scale here.
So the distributed.
Yeah, it just excites a divergence very strongly, and the divergent energy doesn't cascade upscale, but there is some...
Respect from age.
Right. And there is some upscale cascade of the vertical energy, but it doesn't exceed the peak at the forcing. Okay? Now, for these runs, if you shut off rotation, you get no excitation of an upscale cascade. Okay? I just put here the forcing scales for your runs. So the runs you did are dry height forcing at this scale. So they're not exactly comparable, but you also get an upscale cascade of sorts. Okay. So you can understand why the different forcings excite things in a different manner by looking at the moist potential vorticity equation. So if we want to excite vertical energy, if we excite potential vorticity, then it will transfer into vorticity at some point. And you can combine the equations together only for a moist model, you also have to combine the moist equation to get this, a conservation equation for this quantity, so it's F plus zeta, the total, the absolute vorticity divided by not the height, but the modified height due to moisture. And if you work it out, you see that vorticity forcing appears multiplied by H, okay? And adding moisture reduces the effect of vorticity forcing a little bit. We saw that. But it's multiplied only by H. Whereas the height and moisture forcing are multiplied also by the Coriolis force. And the F is much larger than the zeta in our model. So when you set F to 0, these forcings can't excite anything. And so that is why when you shut down rotation, these forcings don't think. And there's...
It's large even though you're at the equator? F is large even though you're dealing with equatorial dynamics?
That's a good question. I guess slightly off the equator. It's
sufficiently large.
yeah. Well, yes. When you look at meridional vorticity advection, the Coriolis force dominates the meridional vorticity advection, the relative advection of vorticity. Yes.
Beta is large. Because beta is large.
Yes. I guess. I mean, I might be wrong, but this is what the equation says, and we have the numerical results. So I think this is the explanation, and it's a good point. So all the zonal mean flow is relatively weak in our model. And also the divergent forcing doesn't appear here in this equation. So it's just not forcing potential vorticity. Okay. The reason why moisture is more efficient than height forcing might be because it introduces memory. We've played a little bit with this. Memory is introduced by different evaporation and condensation timescales, but this is still something we're examining.
This is fun because in your equations, LQ and H play almost the same role, save for the fact that in one of them you had relaxation. In H, you had relaxation.
In H, we have a 500-day relaxation, and in Q, we have two different relaxations, one for condensation, one for evaporation, and they're much smaller. And
so the relaxation time is smaller, so the effect is larger, the term is larger on the equation?
At first, we thought that the fact that you have relaxation, I can go back to the equations. Let's do it this one. At first, we thought that the fact that you have this added term, so you don't have the height relaxation here in the moisture. You have a moisture relaxation in the height. So we thought maybe that introduces some memory to the height or something by forcing this. You're right away forcing the height as well. But then Christian Franzke, who's much more into this, said that the memory is introduced by these being different. And indeed, when we made them equal, then maybe the upscale cascade was slower. I don't remember. But it does make it makes a difference, not in the main.
Equations, right? It's the same relaxation times in both equations.
This and this are 500 days.
Yeah,
and this tau c, is 0.2 days for condensation and 1 day for evaporation.
Could you just explain us why there is a difference between the two timescales for condensation and evaporation?
You mean physically in reality? I know people say there is, and I'm not, I'm afraid to speak in this room about this. But I think it depends what evaporation you mean. I always think that the main evaporation should be from a moist surface as a moisture source, and the condensation is just condensational processes. And that's one possibility. The other is that the vertical, like upwelling, is much faster than downwelling typically. And so if you think of evaporation, but in clouds it's not maybe so. I don't know. But this is just, I mean, this is a very simple parameterization of moisture. And there is no real reason why the two timescales should be the same, I think. Correct me if I'm wrong.
Surely, rain takes much shorter than evaporation, the same amount of water. Now, if you want to precipitate a certain amount of water, it's a much faster process.
The condensation and removing the water is faster than evaporation. But why, in terms of physical terms, I'm not going to.
This is the physics. It's a faster process.
Yeah. Yes, why?
You deplete the cloud within what, 40 minutes? What is that?
Precipitating clouds. If they don't have precipitating clouds, they still have condensation, no rain.
And then they can evaporate. But then it depends how much, whether the downwelling is as quick as the upwelling. And in parts of the clouds it could be, but I think overall it's shorter and also.
Evaporation is a very long process.
These are not dissolved in the models anyways.
Yeah, I mean, it's interesting. There is no real reason to make them the same. I mean, moisture is a non-linear process, and you don't have to make them the same. You can make them the same. The main results don't change, but beyond that, too. But it does make a difference in terms of the moisture variability if you make the timescales different or not. It introduces a memory by having them different. Okay. So we were here. Okay, I don't have a lot of time like I thought would happen, but I do want to show you the super rotation and sub-rotation. So when you look, okay, this is latitude, and you do a zonal mean over the winds in the model. This is what you get for a dry run and moist run. These are 60,000 days of longer runs. Okay, we've gone up to 120,000 days. And red is westerly flow, so eastward, super rotation, faster than the Earth, and blue is sub-rotation. Okay, and you see in the dry run you have these, so these are thousands of days, and the transition itself is a few hundred or almost 1,000 days. So it's a slow transition between super and sub-rotating. People have seen that you run dry models under certain configurations. You get either one or the other. Maybe some runs, typically runs are not as long as, numerical power gets larger. People run things for longer. I haven't seen something like this. I have seen like one transition. But what fascinates me is also this poleward propagation. I've seen it from subtropical jets poleward. I've never seen it from the tropics to the subtropics. So I find this plot fascinating in itself, and we don't understand much of it yet. Hopefully we will. And the moist run is very different. It's super rotating. I mean, most moist models are, and it's stable, no transitions.
So if you had to guess, how should I tune the dry model to produce the same result or similar results with those of the moist model?
There is a simple way to do it, and that is to make the thermal damping much stronger, and I'll show you a run. Okay? So background, okay? You asked at the right time. Just very, very simple background. To get super rotation, you need a moisture convergence somehow, okay? In a shallow water model, it has to be by eddies mostly. Okay? And so you get strong superrotation when you have a source of tropical waves and the momentum damping is not strong enough. One source of damping is waves coming from mid-latitudes and damping the flow. So in our tropical planet, we don't have that. We don't have excitation of mid-latitudes as efficiently as in the tropics. Okay? And in the shallow water model, people have gotten superrotation when they strengthen. Okay? Scott and Polvani had a series of papers when they strengthen thermal damping. And I'll say a few words about why the two are similar if I have time. Okay? So we're going to extend it. There's a lot of existing literature, but just to summarize, and I can't mention them, but we're extending current studies by forcing at smaller scales. Okay? We start from mesoscales. And typically, the runs with mesoscale stochastic forcing are at larger scale, like the group here did. So we start at smaller scale. So we allow this clear upscale cascade to be what forces these rotations. And we add moisture in the shallow water setup. Okay, so we have ensembles of 2,000-day runs, where the last 1,000 days are equilibrated, and we have long integrations, okay, and I showed you 60,000 days. So when you do this, and we can vary the degree of coupling, this L that comes in front of Q in the height equation, you can set it to 0, you can set it to the value I showed you, and you can double it, okay? So the dry is red, the runs I've showed you, we call weak moisture coupling, are in gray, and strong moisture coupling is in blue. And here you see the mean zonal wind, okay, at the equator as a function of time. We start with no wind, and the wind either decreases to subrotation or increases to superrotation, or in the middle, and here you see the distribution. So the more moist you are, the more superrotation you have. Okay? And if you look at the momentum budget to see what distinguishes that. So here I'm going to show you only the dry and the moist, the weaker moist run. This is the eddy momentum flux convergence and the wind. Okay, eddy momentum flux convergence and the wind for the moist model. In the dry model, we just take the sub-rotating runs. Okay, and we see that eddy momentum flux convergence is what drives things. There is this FV star term, which is larger in the super-rotating runs. Okay, in the subtropics, you don't see it in the sub-rotating runs. Okay, so the equatorial jets, eddy momentum flux convergence drives them, and thermal and Rayleigh damping is what balances them. Okay. So now I just want to show you what the eddies look like. And this is a snapshot. Okay, we've looked at a lot of these, but this is a snapshot from the dry sub-rotating run. Okay, and you see many, many scales and eddies. And what you see here, okay, so this is the eddy field. We've subtracted the zonal mean. We've subtracted the zonal mean wind like that. But you see an eddy with very strong equatorial easterlies. Okay? And you see another eddy with equatorial westerlies. Okay? In fact, we chose this longitude because this is the strongest equatorial westerly in this plot. And we can choose the strongest negative U along the tropics. It would fall here. Okay? And we can actually do this for we take every 10 days out of the 1,000 runs of every one of our ensemble members. And we center them either at the strongest zonal wind or the weakest zonal wind to look at these. So what you see here, actually, these are Rossby waves, but they're wave packets. It's not a Rossby wave that goes around. You have a wave packet where it's dominantly two highs. Okay, the color is the height field, and so two anticyclones, or it's dominantly two cyclones in this Rossby wave packet, and you see a whole bunch of other waves. Okay? And you can do this, center these figures and composite these waves. So this is what the negative wind eddies look like typically in the subrotating dry case. And this is what the positive wind at the equator look like in the subrotating case. Okay? And now what we do is we look at the eddy momentum flux of each of these snapshots. So instead of calculating the height or the rotational spring function, which is shown here, we calculate the meridional eddy momentum flux, U prime, V prime. Okay, how much momentum is fluxed in this direction. And then we can composite this field, and this is what we get. Okay, so looking at these, this pair of anticyclones, you get positive eddy momentum flux here, and negative here, and negative here, and positive here. If you zonally average over this, you think you get 0, but there is some difference in the strength. So there is a systematic contribution. And so what we do is we average over the region of the eddies, just the meridional eddy momentum flux. We do this both for the same signed eddies, so the eddies that have subrotational flow in the subrotating case, and the oppositely signed eddies, eddies that have superrotating flow in the subrotating case. And we do this for all cases. And this is the last graph I'll show you. So in the dry, and now we look at runs that have subrotating in the dry. Those are in blue, and superrotating in the dry, and the same for the moist. And the blue curve is an average of the eddy momentum flux convergence, so what they do to the flow in eddies that have the same direction of flow as the zonal mean. And this is in colors, and the black lines are for the eddies that have the opposite direction of flow. So one thing we see is, especially in the moist runs, both kind of eddies contribute the same and strengthen superrotation or strengthen subrotation in the flow, meaning the zonal mean flow tilts the eddies with it. But it does so more efficiently for the eddies of the same sign. And this is just the zonal momentum flux convergence in the eddy region. And so the eddies that have the same sign of the mean flow get strengthened by themselves. The flow at the equator of the eddy gets strengthened more strongly than the eddies of the opposite sign. And so this is some kind of stochastic selective eddy feedback that we think is occurring here that makes the eddies that have super rotation at the equator get stronger, and so they dominate the zonal mean flow. And this is a very slow process. The differences are small, but the transition time scale of 1,000 days fits this difference here, for example. And you see that in the moist run, the subrotating eddies in the superrotation dry flow don't do anything in the tropics, but in the moist run they do. So the moist run, somehow the eddies are more organized. You see the same thing here, to enhance this superrotation. Okay, I don't have time. There is a little bit about why things are stable or not in the moist run. I will just say that we think it has to do with meridional fluxes. And if you look at the mass balance, then convergence of mass has to be balanced either by heating or cooling, thermal heating or cooling, or moist processes. So if you strengthen the thermal damping, this is what you get. You get superrotation. Okay? And why moisture has larger mass flux?
Tau H is larger or smaller?
Tau H is smaller, yeah.
That makes sense.
Yeah, so there is something about allowing divergent modes in the moist run or strong thermal damping.
So it's unclear why moisture, which obeys almost the same equation as height, with tau h of infinity, no? 1 over tau h,
yeah, it's
1
small.
over tau q of 0, I should say, right? In your q equation, 1 over tau q, let's call it tau q is 0.
It's tau is 0.2 or 1 day. It's not.
In the moisture, you didn't have this term, this relaxation term.
Yeah, I did.
In Q?
Yes, I will show you the equations. Okay. So this is the question session, right? Because
Maybe we should let Nili finish though.
Yeah.
Getting later.
These are the equations.
So there is no relaxation.
This is.
No, H minus H, and your relaxation will prescribe it.
Ah, okay. I wrote the equation for the mass balance for HV. It's the H equation that.
Right, I understand. For the H equation, you have a relaxation to specify distribution.
Right.
Okay, let's do some.
Okay.
Sorry, I'll shut up. Try to shut up.
Summary. I need the right summary. Here. Okay. Okay, so I showed you that mesoscale stochastic forcing can excite an upscale vorticity, vertical kinetic energy cascade that gives rise to a red noise background spectrum and linear modes. And what matters is how efficiently you excite vorticity, and the effects of the different types of forcing can be understood through excitation of vorticity through the moist potential vorticity equation. And we also saw spontaneous transitions between super and sub-rotation in the dry run and not in the moist run. And we think it's a systematic cumulative eddy feedback of the eddies on themselves. When you have Rossby wave packets, which are what dominate the variability, there are some interesting things about differences in the Yanai waves, which I'm not sure about, but those are divergent modes. But we think the role of moisture is through the ability to excite or an effect through the divergent circulations and divergent mass flux. We're not sure about that. Okay. I will say thank you just to say that GCMs are different in many ways. Okay, the results are, but the main ability to excite this upscale cascade is the same, but the dependence on moisture is very different because the radius of deformation in a GCM can decrease, not increase, because of effects on the stratification, which different effects on stratification. Okay, and superrotation in GCMs, you can have GCMs doing the same set of runs, one getting superrotation, one not, depending on the numerical scheme of the momentum. Okay, thank you.
Thank you very much. We're pretty much out of time. If anyone needs to leave, it's time to stay. If we have a quick question.
There's email if someone. I always find myself, needing to absorb talk. So sometimes I only have questions later.
But if different GCMs give different results, what can you say about the conclusions?
So the nice thing when GCMs give different results is when you can explain it. So if you know that one GCM, for example, there are sets of runs I did with Jay Sukatme, with two different students. They ran a model that had a tropical planet configuration. And in one case, you get superrotation, and in the other, no. But you know that one GCM has a much more diffusive momentum budget. And that's the one that didn't give you superrotation. So I mean, beyond figuring it out why there is a difference, I mean, gives you richer. So